The path of a particle that's moving in 3D space can be defined by the following vector-valued function. So we have the position vector measured from the origin as a function of time is equal to the x component of the position of the particle as a function of time in the x direction plus y as a function of time in the j direction plus the z coordinate as a function of time in the k direction. And over some time interval, t can be in the interval being the initial time to the final time. So for example, if we consider this vector, the position vector at time t0, and some other position vector at time tf, then the position vector traces out the particle's path over this time interval. So essentially, the vector-valued function on a domain set D is a rule that assigns a vector in space to each element in that domain. So our domain here is the interval of real numbers t, which results in a space curve. And t can refer to time or any other real quantity. So here, the particle's position along the curve has the coordinates x at time t, y at time t, and z at time t, being the components of the position vector. And these components, where x is a function of the parameter t, y is another function of the parameter t, and z is another function of the parameter t, these component functions parameterize the curve from some time t0 to a final time which gives the interval. So x of t, y of t, and z of t are called real valued functions because they take a real number as an input and output a real number, and these are components of the vector valued function r, which takes in a real number and outputs a vector. We can extend limits and continuity from real valued functions to vector valued functions. So if we're given a vector valued function of a parameter t being equal to x of t in the I direction plus y of t in the j direction plus z of t in the k direction, and if this vector valued function has a domain D, so the domain of R is D, and we have a vector L, then the limit of R of t as a parameter t approaches a value t0 is equal to L when the limit of x of t as t approaches t0 is equal to the first component of the limit, which we'll call L1, and similarly the limit of y of t as t approaches t0 is equal to L2. Let's move this across. And the limit of z of t as t approaches t0 is equal to the third component. So this is the informal definition of the limit of a vector valued function. And the epsilon delta definition is extended in a similar way from real valued functions to vector valued functions. So for example, if this is r of t0, then we check the limit from both sides as we did for real valued functions, to see if the limit exists. And similarly, a vector valued function r of t is continuous at a point where t equals t naught in its domain if the limit of r of t as t approaches t naught is equal to r of t naught. Given the position vector of a particle r of t, which is equal to x as a function of time in the I direction, plus the y coordinate in the j direction, plus a z component in the k direction. And if the functions x of t, y of t, and z of t are differentiable at time t, then by vector addition, given that this is r of t, and this vector is r at time t plus delta t, then we have r of t plus delta r is equal to r of t plus delta t. And therefore we can write delta r as r of t plus delta t minus r of t. So in terms of their components, we can write delta r as x of t plus delta t minus x of t in the I direction. And similarly, we have y at t plus delta t minus y of t in the j direction, and plus z of t plus delta t minus z of t in the k direction. And now if we divide the equation by delta t, so we have all these terms on delta t and the z terms, and we take the limit on both sides as delta t goes to 0. So we have the limit of delta r on delta t, well, the limit of this term as delta t goes to 0 is equal to the first derivative of x with respect to time, because the unit vectors representing the axes do not change in magnitude or direction with respect to time. And this term becomes dy dt in the j direction, and the third term is the rate of change of z with respect to time in the k direction. And this term on the left hand side is the derivative of the position vector with respect to time, or the parameter t in general. So essentially, when q approaches p, then this secant vector approaches the tangent vector to the curve at point p. Now if r is differentiable, then it's differentiable at every point in its domain. And note that the curve traced by r is smooth if the derivative of r with respect to t, or r dash of t, is never equal to 0, and the derivative is continuous. So when r dash of t is equal to 0, the slope of the tangent to the curve becomes infinite. So essentially this means that the component functions x of t, y of t, and z of t have continuous first derivatives that are not 0 simultaneously, or at the same time. So similar to real valued functions, a smooth curve means there's no sharp corners or cusps, and you can also have piecewise smooth curves, such as this one, which is made up of a finite number of smooth curves that are connected together continuously. While these curves are not differentiable at these points where the derivative changes abruptly, so being points A and B. Given a position vector of a particle that's moving along a smooth curve in 3D space, in some domain where t is between t0 and tf, then the velocity vector, which is v as a function of time, is the first derivative of the position vector with respect to time. So this velocity vector is tangent to the curve, and the speed is defined as the magnitude of the velocity vector at time t, and the acceleration is the first derivative of the velocity with respect to time, or the second derivative of position with respect to time. So when the curve is smooth, dr dt is never zero, so the particles never stop or reverse direction. And we can also express the velocity vector as the speed multiplied by the direction vector, given by v on its magnitude. So we have speed by a unit direction vector, being the direction that the particle is traveling at time t. The rules for differentiating vector-valued functions are similar to those for scalar-valued functions. So if we take the first derivative of a vector-valued function that's constant, then that gives the zero vector. And if we take the derivative of a scalar multiple of a vector-valued function, which is a function of the parameter t, then we can take the scalar outside the derivative. So we have the scalar by dv dt. And taking the derivative of some function of t by the vector v of t by the product rule gives f dash of t by v of t plus f of t by v dash of t. And similarly, the sum and difference rules are where the derivative of the sum of two vectors, or the difference between the vectors with respect to t, is equal to v dash of t plus or minus the derivative of w with respect to t. And the product rule also extends to the dot and cross product. So if we take the derivative of the dot product between two vectors, which are both a function of t, then by the product rule we have v dash of t dot w plus a dot product between v and the derivative of w with respect to t. And similarly, for the cross product, taking the derivative of the cross product between two vectors gives a similar result by the product rule of differentiation. So we have v dash of t cross w plus v of t crossed with the derivative of w with respect to t. And finally, if we have the derivative of a composite vector valued function, so v as a function of f, which is a function of t, then we can take the derivative of v with respect to f first and multiply this by the derivative of f with respect to t. So we're basically chaining these derivatives together. And that's the same thing as writing v dash of f, which is a function of t, multiplied by f dash of t. If we have a vector valued function with a constant length, so the magnitude is constant, so that means the squared length is also constant. And the squared length is the dot product between a vector and itself. So for example, if we have the path of a particle on the surface of a sphere, then the radial distance to the particle is always constant. And now differentiating both sides by the product rule, we get r dash of t dot r of t plus r of t dot r dash of t is equal to 0. So therefore we get 2r dash of t dot r of t is equal to 0, or the dot product between the derivative and the vector valued function is equal to 0. So this is the velocity vector and this is the position vector, and these vectors are orthogonal. And this is true for any differentiable vector valued function with a constant length. Sketch the curve given by the following vector valued function. So we have x of t is cosine t, y of t is sine t, which parameterize a circle parallel to the xy plane, and z is equal to t, where the position of the particle increases linearly in the vertical direction. So if we take t equals 0, the position of the particle is at x equals 1, y equals 0, and z equals 0. So this here is our first point on the curve. And when t equals pi on 2, we have 0, 1, pi on 2. So our next point is at x equals 0, y equals 1, and z equals pi on 2. And if we take our parameter t to be equal to pi, the position of the particle is at -1, 0, and pi. So that'll be somewhere around here, and x equals -1 and y equals 0, and at z equals pi is around here. And if you also take the derivative of the vector valued function, we get minus sine t in the I direction plus cosine t in the y direction plus 1 in the k direction. So our helix would look something like this. So it twists in a circle while the height increases. So we can see the derivative at t equals 0 pointing in the positive y direction and the positive z direction, and at t equals pi on 2, the tangent vector points in the minus x direction and positive z direction. And at t equals pi, the tangent vector points in a negative y direction and positive z direction. And this continues on and on. Find the velocity, speed, and acceleration of a particle where its motion in space is described by this position vector. So the velocity is the first derivative of the position vector with respect to time. So we get minus sine t in the x direction plus cosine t in the y direction plus 1 in the z direction. And the acceleration can be obtained by differentiating the velocity. So we get minus cosine t in the I direction minus sine t in the j direction plus 0 in the k direction. And the speed is the magnitude of the velocity, which is the square root of minus sine t squared plus cosine t squared plus 1 squared. So sine squared t plus cosine squared t is 1, so that gives root 2. Graph the cycloid and find the maximum and minimum speeds and magnitudes of acceleration. So if we take the derivative, we get the velocity or the tangent vectors to the curve at t. So that gives 1 minus cosine t in the I direction plus minus sine t in the j direction. So at t equals 0, we have the position along the cycloid being x equals 0 and y equals 0. So that's the position. And the velocity has components 0 and 0. So the tangent line here is vertical. And when t is an odd multiple of pi, we get the position having an x coordinate of n pi and a y coordinate of positive 2. So cosine pi, 3 pi and so on gives negative 1. So we have at pi 3 pi and 5 pi, a y position of 2, and a velocity with an x component of 2 and y component of 0. So the tangent vector points horizontally at these points. And for even multiples of pi, we have a position of n pi, and 1 minus 1 is 0. So at even multiples of pi, the y coordinates are 0. And as we said at t equals 0, we have an undefined derivative and a position of 0. And also for even multiples of pi, our tangent vectors are 1 minus 1 is 0, and sine of 0 is 0. So our derivative is also undefined at this point. So we have cusps at even multiples of pi. So our curve will look something like this. So it'll be half ellipses that look like this, and that's a cycloid. And to find the maximum and minimum speeds, we take the magnitude of the velocity. And here we'll take the squared magnitude first. So that gives 1 minus cosine t squared plus sine squared t which is equal to 1 minus 2 cosine t plus cosine t squared plus sine t squared. And cosine squared t plus sine squared t is 1 by the trig identity. So what we get is 2 by 1 minus cosine t. And taking the square root of both sides, the speed is the square root of the right hand side. Now the maximum speed is obtained when t is an odd multiple of pi. So we get 1 minus cosine pi, which gives 2, by 2 is 4, so root 4 is 2, which is in units of length per time, and the minimum speed is obtained when t is 0 or an even multiple of pi. So that gives a minimum speed of 0. Now the largest magnitude of acceleration can be obtained by differentiating the velocity. So we have the second derivative of position with respect to time is equal to sine t in the horizontal direction plus cosine t in the vertical direction. So the magnitude of the acceleration is the square root of sine squared t plus cosine squared t, which is root 1 or 1, which is in units of length per time squared. So this is both the maximum and minimum magnitude of acceleration.